Hello everyone, my name is Mohammed Saleh and I'm from ICOA2025 University. Today I'll be presenting our research on addressing security gaps in a model context protocol, where we will propose a design for a resilient reference architecture to make AI agents safer and more reliable. So for the plan, we will go over what is the model context protocol, look at its architecture, and present our key security findings we did identify during our research, and we will propose a resilient reference architecture with the performance analysis and conclude with our key findings. So what is the Model Context Protocol, or MCP? It's simply a new standard designed to solve a major challenge in AI, enabling large language models to interact seamlessly with external tools and data sources. So for example, before the introduction of MCP, developers had to build a custom unique API for each external service to use their tools, which was complex and didn't scale well. So after the introduction of MCP, we can use multiple external services with a standardized intermediary, which is the MCP protocol. This simplifies development and creates a more robust ecosystem for AI agents. So for the architecture, we have mainly four components. The MCP host, which are applications such as an IDE, like a Visual Studio Code, where it can interact with the large language model. The MCP client that runs in this MCP host, which manages the communication with the various MCP servers. We have the MCP servers, which are crucial piece that exposes tools and data that can be used by the large language model. Now let's move on to the security challenges. The first major threat we did identify is tool poisoning. For example, here we have a rug pull attack, where a server has a tool which is benign, but it can be changed randomly at any time to include the malicious instructions. So for example, here we have on the right side a prompt injection attack that was added to this tool that instructs the large language model to hand over sensitive data that is stored in .env without informing the user whatsoever. The second attack is name squatting, which is basically similar to domain squatting, where an attacker can register a MCP server that is similar to a legitimate MCP server. It can have basically the same functionality, but it can also have some malicious functionalities, such as stealing sensitive data that was supposed to be submitted to the legitimate MCP server, or much worse, injecting malicious instructions with the users of prompt injection, such as what we've seen before. Injection attacks are also a security challenge for MCP. For example, command injection and SQL injection vulnerabilities are still found to be present in MCP server implementations, and prompt injection attacks are significantly more complex and harder to prevent due to how large language models inherently function. Basically, they can't differentiate between instructions and data. Other security challenges we did identify is the weak authentication in MCP servers. For example, the widespread usage of static API keys with indefinite validity. And also we did find that it is possible to exhaust resources in an MCP server if there is no rate limiting, for example. So for the proposed reference architecture here, to fix weak authentication, we propose the use of OpenID Connect for secure short-lived tokens, role-based access control to ensure users can only access authorized tools, rate limiting that prevents those attacks and resource exhaustion, and the uses of a web application firewall or a WAF to filter malicious traffic, such as SQL injection, and finally a prompt shield provides a critical defense against prompt injection attacks. So after implementing this reference architecture, these are the results that we did find. The security that we did implement comes at a cost, where we can measure a performance overhead of 15 to 20% in our controlled test environment, and we estimate that 15 to 30% estimated overhead in real deployments. Now we will move on into the proposed prompt shield. So, for example, we did propose this architecture for a prompt shield. It is composed of 3 layers. We begin with a simple pattern filtering, semantic search, then large language model analysis. The first layer is intended to catch known attacks using simple rejects patterns. The second uses semantic analysis to detect more harder to catch threats that might be phrased differently but have the same meaning. And the final layer uses a specialized large language model for sophisticated analysis of anything that can still look suspicious. To build our prompt shield for the first layer, we collect known attack patterns from public resources. For the second layer, which is the semantic search, we use a machine learning algorithm to extract semantic sentences from a large dataset of prompt injection attacks. These semantic sentences will be used for semantic search to determine whether user's user's prompt is malicious or not. For the final layer, we use any large language model with good reasoning to determine whether user's input prompt is malicious or not. After implementing our prompt shield, we did evaluate it against public datasets of varying languages, 2 in English, 1 in Vietnamese, and other in Turkish, and other top performing models. So across our benchmarks, we can see that our model did perform consistently across these datasets, and it has closer scores to other models. This is all while being faster in inference time. We can also note that further improvements in semantic sentence extraction in the second layer can be significantly enhanced in the future. So, in conclusion, our research highlights that while the Model Context Protocol is a powerful new standard, it introduces complex security risks. In response, we designed a resilient architecture that mitigates these threats. Our solution is both effective and practical, with a performance overhead that represents an acceptable trade-off for robust security. Thank you for your attention.